Okay, this is the first homework problem of the first homework assignment. I will be going through the process step by step, including all the problem solving procedures. I recommend that when I get to a location, if you're watching this video looking at your homework notes and you stopped at the point I've gotten to, then take a pause in the video and see if you can figure out the rest of it before I give you the next step. Okay, so when I do something new that you haven't gotten there yet, pause the video, see if that one step I gave you allows you to finish it on your own. If not, then just hit play and continue on. But the whole point of the video is to help you get a little, push or nudge towards the right answer so you can finish it on your own. So, starting with basically understanding what the question's asking is really important. So you need to start with a diagram, okay? And your diagrams need to be carefully drawn so that it's easy for you to know what you're being asked to do, and it's easy for me to understand that you know what you're being asked to do. Okay, so some people think at the beginning of the year that drawing diagrams is a waste of time, and they learn the hard way that it actually saves you a lot of time when you're making mistakes. So the diagrams do not need to be, works of art. I'm going to have the school that the car starts at over here, and labels are always good, so you have the school. And I'm going to have the car because he starts here. Again, no points for anything fancy. Okay, don't even need a windshield if I don't need a windshield. So the car was driving towards a house. Okay, trying to go home. So you have nice house over here. And between the school and the house, there was a location where the car came into a cloud. It was raining and had to slow down as a result. So you got some raindrops here, and at some point, the car gets to this location. Okay, that's basically the diagram that you need. Okay, you might want to label home here. Uh, you could technically label rain, but I think I did a good enough job on the drawing there. You guys can judge that for yourselves. Once you've done this, I'm going to draw a road in here just to make it easier to use the line as a reference. The car started from the school, so I'm going to label the location over here where they started as X initial. And because I'm using that as my reference, that's 0 meters. They also told you the car's initial velocity. So my velocity in the X direction initially was 95 kilometers per hour. Now that's not the standard unit, but we're not going to worry about that yet just yet. We're just going to write down everything that we know from the problem. Now there is a issue with your equation sheet and this problem because the equation sheet likes to use initials and finals. But this problem actually needs to have two final positions. So there are two ways you can do this. You could say that you have x1 for this final position, and you can have x2 for the home. Okay, you can do it that way. Some people like it better that way. Um, Personally, I like to use letters. Okay, so I would use XR for the position of the rain, and then I would use X1 for the final position. Okay, it's up to you. I've noticed that more students seem to appreciate using ones and twos because it's easier to put them in order instead of trying to remember where the letters go. So I'll stick with the ones and twos in this case. But if you prefer to change all the ones that I write down to R's for rain, and you change the twos to a one, that's fine. You can even keep the one, change the one as a R, and keep the twos just the way they are. It doesn't really matter. When you have it labeled in the diagram, everybody knows what the variable is. That's the additional point of drawing a diagram, is you don't have to match the equation sheet as long as your equation and your diagram agree with each other. Now before we go on with more labeling, we need to label a direction for positive. So I'm going to say going to the right is positive. I'm going to do that right on the diagram so everybody can see it. It makes it easier to follow along. And this position here where the rain started was positive 130 kilometers. We're not told this final position, so that's just a question mark, which is actually what we're looking for. And you have a velocity here in the x direction, and we're just going to say that's Vx1 just to match the position, and that was a positive 65 kilometers per hour. And I'm just realizing I made a mistake over here with the 95 kilometers per hour. I should have put the addition sign way over there. Hopefully you caught that. If not, it's all right. So we have a positive 95 kilometers per hour. It's okay if you don't catch signs like that. That's the reason why you write all the variables and then you're supposed to check for signs and your units. So if you didn't catch it before I did, that's okay. That's the reason why the steps are in the order they are. Now we have the position of velocities listed. We don't have a velocity for when you get home. It's not needed because when you're home, you've arrived, it's going to be zero. You're going to stop. Okay? Hopefully you don't drive into your house. We do need to label all the time though. Okay? So this time at the beginning is t0, your initial time. That's going to be 0 seconds. We're going to keep track of our time from that reference point. We also, there's a point in time where they get to the rain. We don't know what that is. And there's a time when they finally reach the house. And they tell you that's 3 hours. I'm going to have to zoom out for this to fit. And 20 minutes. There's nothing else that we know. Okay, that's everything they give us in the problem. That's what your diagram should look like. Those are the variables. Before we move on, we need to convert anything that's non-standard unit. Okay, so first thing I would change is I change all the positions. So first position that I see as an issue is x1. So if you look here, we have 130 kilometers. So I'm going to change my pen here to blue, and I'm going to show here the conversion. Now obviously when you're doing this in your homework, it's not going to be color coded. I'm doing this to help you guys out. I don't need it to be color coded in order to correct your homework or to check your homework. So you have 130 kilometers. That's going to equal a positive 130,000 meters. Okay, so there's one conversion down. The next conversion would be the let's see if this is too dark. Nope, not too dark. So the next conversion would be the initial velocity in the x direction. So we have Vxo equals. Now I wrote it in a line on the top to save space, but I recommend that when you're doing the conversion, you actually write them over each other. So you write 95 kilometers, it's positive, over 1 hour. I notice that some people who have issues with conversions have an easier time when it's written like this. Now that's the same as saying 95,000 meters over 1 hour. And then we have to convert the hours, so we're going to multiply. So we put an hour on top, and the unit we want is seconds because we want meters per second for velocity, so we're going to put seconds on the bottom. And you have to think, well, how many seconds are in an hour? Now, you may not know this yet, you haven't memorized it yet, but You have 60 minutes and an hour and 60 seconds and a minute. So if you just do 60 times 60, that's the number of seconds in an hour. So 3,600 seconds are in an hour. If you don't have that memorized yet, you will have that memorized pretty soon because you're going to be doing that quite frequently in this class. So you do 95,000 divided by 3,600, you're going to have a positive 26.39 meters per second for the initial velocity in the x direction. Keep in mind that I have four sig figs listed at four significant digits because I only need two for my answer. I have 95 kilometers per hour, 65 kilometers per hour. Those are both two significant figures, okay? So as long as you have an additional two significant figures in, added to what your final answer needs to be, you will not need to worry about any kind of rounding issues. It won't cause an issue for your final answer at the end. So I only need two significant figures for the final answer, so I'm using four significant figures for my calculations prior to my answer. That only gave me the initial x velocity. Now I need to do the same thing for the final, or I shouldn't say final, but the velocity when it started to rain. So we need to do another conversion. So you have Vx1 equals a positive 65 kilometers. And again, I would write the hours underneath. Let's move this up a bit. So we know, just like before, that's going to be a positive 65,000 meters over an hour. You can multiply that by 1 over 3,600 seconds, because that's the number of seconds in an hour. And when you do 65,000 divided by 3,600, you get a positive 18.06 meters per second. Okay? We have one more conversion. We need to convert the time. So right here, the time is given us in 3 hours 20 minutes, which definitely is not going to be used. We need seconds. So let's go ahead and move down. We have t, and this is t2, it's the final time, was 3 hours and 20 minutes. You can do this a couple ways. I think the easiest way is to just figure out how many minutes you have first. So you got 3 hours times 60 is 180 plus the 20, so that's 200 minutes. Then you multiply the 200 minutes by 60 seconds, so you get 12,000 seconds. That concludes the conversions. Okay, so that's everything you need for the conversions of the variables that you were given. Now, for part A, they want you to determine the total distance that the car traveled. In order to do that, the first thing you need to do is calculate the time for the first part of the trip, so you know how long the person was driving at 95 kilometers per hour and how long the person was driving at 65 kilometers per hour, so you can figure out the total distance, because we know that they were driving 135, we know they were driving for that first 130 kilometers, that they were going 95 kilometers per hour, but we don't know how long the person had to drive at the 65 kilometers per hour, and that changes how far the home is. So to start, you want to identify the equation. I'm going to switch back to black. The equation we're going to use is the standard equation for velocity. Now, I'm going to write out the standard equation, and then we're going to rewrite it so that we're looking at the terms we know. So velocity is, actually, you know what, I'm going to write it over here on the right because we're going to use it multiple times. So velocity is delta x over delta t. That's true of all cases. Now we have to take that equation and plug in the variables for what time and position we're talking about with the appropriate velocity. We are trying to solve for t1 in this case so that we can figure out x2. Okay, so it's a multiple step problem. So if we're using that, we're going to be changing this equation, so we're looking at v x initial is going to equal the position that velocity describes. So final position in that case was x1, and the initial was x with a subscript 0, x initial. And time was t1 minus t initial. Now at this point, it's a good idea to cancel out any zeros. So x initial was a 0 and t initial was a 0. So we can rewrite this as Vx initial equals x1 divided by t1. Multiply t1 to the left side and divide by the velocity, and you'll get t1 equals x1 divided by Vx initial. So we multiplied t here over here, we multiplied it there, and then we divide Vx initial so it comes back down here. Okay, so this equation t1 equals x1 divided by Vx initial is going to give us our answer. It's isolated now, so we can plug in values. So the values, you get t1 equals, and you want to make sure you're using the values that you converted. So you have a positive, I don't know why that's so messy. There you go, positive 130,000 meters all over. And the velocity, you need to make sure that you use the velocity for x1 initial, not x1 final. So it's Vxo, not Vx1. Vxo was the dark green one, that's positive 26.39 meters per second. Okay, so that's the equation with the values. When you divide those, you'll have that t1, I'll go back over here, t1 equals positive 4,926 seconds. So that velocity from the 26.39 is just the velocity from the car leaving the school getting to the rain. And so that velocity that we used from the school to the rain is what's used to figure out the time from the school to the rain. Okay, so now we know the time t1. Where's this? So this time right here, wrong marker, sorry about that. This time t1 is this value right here. So we have a new piece of information that we didn't have before. Now, this is an important piece of information because we already know the total time, and now we know the time to get to the rain, and we can subtract the total time. Okay, let me show that algebraically actually. So the new equation that I'm describing is that the total time, so you can write it multiple ways. You can just say t, and write total, is going to equal, So I'm saying that t total is the whole time it takes, so that means it equals t2. But the total time also really means you're going to take t1 plus, whoops, t1 plus the change between t2 and t1. Let's see. Which might be a little confusing. What I actually like to do is think of it as you have your final and you had your time in the where the rain started. So all you really need to do is say basically what you want to end up saying is that you have the change in the time from t1 to t2. So you have t2 here. That's going to equal t2 minus t1. Okay, so really what you're describing is that, is this the same color? Yeah, it is. Here we go. So from here to here, okay, that green area I just selected, I made the pink turn brown, but that's okay. That green area I just highlighted here is describing this. Okay, we need to know the time it took to go from T1 to T2. So if we just subtract T2 minus T1, we'll find it. Okay, I think personally that this is the better way to think about it. So I'm going to go ahead and erase this top one now. So you're just looking at the total time. So if you take this time here, you take the change in the time, you take the velocity and the position like we did before, but this time you're solving for the position at the end because we know both time scales that are on the bottom. So going back to an equation, we're going to use that first equation that we had right here. Okay, and all you're going to do is change the variables to talk about the second part of the motion of the object, which I'm actually going to do on the right because I don't want to keep scrolling down because there's a whole nother section to this question. So we will have the velocity be vx1, and we're still talking about change in position over change in time, but the position this time is x2 minus x1 over, and the time is t2 minus t1. Plug the, oh, I'm sorry, you have to isolate it. So we isolate, we're going to first see if there's anything that's a zero. In this case, nothing's a zero because they all start with a value. Okay, so it's going to require more algebra than last time. We'll multiply the time to the left and then add in x1. So you'll have v x1 times t2 minus t1 would equal x2 minus x1. I'm going to go ahead and just move this over to the right. Once you've done that, you need to add x1 to the left. So you'd have a final equation of x2 equals vx1 times t2 minus t1 plus x1. That would be the equation you need to figure out the position. Plugging the values in, let's see if I can zoom out far enough. No. Okay, so I'm going to do a trick then on the computer that will allow me to just move it over. See if this works. And see if we go down. Okay, so I just moved the equation down to the bottom so that way I can look at the values a little easier. Again, in case moving it confused you, we are looking at this equation here. Vx1, so I'm going to start it down here. X2 equals Vx1, which was a positive 18.06 meters per second. T2 was that time that we were originally converting, that 12,000 seconds. And then T1 was the time we just found, which was that 4,000. I just realized I don't know why I put a plus sign over here for 4,926, but it should not be there. It should just be the number. Yeah, 4,926 seconds. So we have 12,000 minus 4,926 seconds, and then we need to add x1, which was that 130. So 130,000 kilometers. Now that is a displacement, so it does need a sign. So you put that in the parentheses with the sign. And the value you should find that the total distance will be 257,800 meters. Okay, I'm sorry, I jumped ahead. That's not what you get from that equation. That's actually the 127,000. Sorry about that. So 127,800 meters. I'm gonna double check that real quick. So we take No, I was right the first time. I'm sorry. So the left side is that, and then you add the 130. So I was right the first time. So you get 257,800 meters. That's the total distance from the school to the house. Okay, so that's your answer for part A. Now, when you write that, you shouldn't stop here because you need to have it with scientific notation and significant figures. So this will actually be 2.6 times 10 to the fifth if you kept it in meters, or you could write it as 2.6 times 10 to the second if you had it in kilometers. Okay? Now the next one, part B, is actually really easy. They're asking for you to find the average velocity. Okay, so this won't take nearly as much time as that last one did. We have our position, and like we know the total distance, and we know the total time it took. So with the total distance and the total time, we'd be able to figure out that the equation, first of all, is just going to be the average velocity equals the change in position over the change in time like before. Okay. Delta x is just the total distance, so because you started from 0, so when you have the v average, you're really looking at x2 minus x initial over t2 minus t initial. But as we said before, those initials are 0, so we can find the average just by taking that total distance of 2.6 times I'm sorry, you shouldn't be using 2.6. Technically, you should use the 257,800 meters, because you don't want to use the rounded number because it will round your final answer, and you divide it by 12,000 seconds. So again, I plugged in 257,800 meters because we want the number that's not rounded, because we're finding a new answer, okay, a new value with the number that we actually calculated. And you should get an average velocity of 21.48 meters per second. If you're going to have that with sig figs, your average velocity would be 21 meters per second. Okay, now you go back, circle your answer, so that's an answer, and here's your second answer. Just to make it easier for me to find the answers, I see a box, I know it's an answer, and you would answer this in a sentence. You would explain that you know you're going to have the position for the house located a distance from the rain. Okay, you don't know what distance it is, but you can find that distance by figuring out how far did it travel from the 130 kilometers to that final position of the home, and you add that 130 to it. Now we already did that in the equation. You didn't have to put it if you didn't use this equation originally. You could have found just the one location and added to it, which is why I wrote down that 127,800 at first. I forgot that I already put in the 130 kilometers in the video, because when I did it on my own on the paper, I did it a little bit differently. But the key here is you're going to have to add in that extra amount to get the total distance. Either do it in the equation from the beginning like I showed you in this video, or you might have done it separately and added it in later, which is okay. As long as you got these values, you should be fine. There, again, it's multiple ways you can do these problems, but this is the most straightforward and direct way, I think, to get to the solution for these two sections of the problem. This concludes the first question, and I'll be going through the other questions in a separate video.